going to do real quick is I think just to show the assignment structure, I'm going to swap to this one. Is that cool, GV? Do you mind if I do this one just because it has the assignment? Okay, cool. Yeah, this one isn't much different. You have n starts as its initial value. We set some variable I to start at 0 at the beginning. And then while m does not equal I, we're going to keep adding 1 to I and keep adding 1 to n. So because I starts at 0, we should expect this loop to repeat m times, right? You're going to keep adding 1 up until m, which means we're going to add m to n once again. And we should end up with, like before, right? All of these are called adding for a reason. This loop should end up setting n to be equal to its n's initial value plus m, right? So this is just a loop that's designed to add m to n. Okay, so once again, we're going to start proving. Okay, so start with what you have on the top and bottom. And then you are going to, or sorry, I'm doing this wrong. I am doing this wrong, aren't I? Nope. I'm doing this correctly. Okay, now we need to set up our assignments. This you just have to memorize the structure for. It's just annoying. If you have any commands at the top, you just do them like this. There's not much more to say. I have just memorized this from doing enough while loops. You do assignment with substitution. And you need to reach what we're going to call Q. This is our invariant, all right? Whatever your invariant, okay, just to make sure we actually understand what the invariant is. The invariant is some mathematical property that holds at any point in the while loop, meaning it needs to hold at the moment the while loop starts, and it should hold at the end of any iteration of the while loop, and it should hold once the while loop exits. So you just really what you want here is the strongest mathematical property that holds in all of those cases. And I'll talk a bit more about what that's going to be like for this loop once we have the bit of the structure set up. But you need to prove, first of all, that your invariant holds in the initial state. That's what this task is. It's like, okay, after I do all the commands, does my invariant actually hold before the loop even starts? Then you start doing, oh god, do I even remember how to do this? We have to do our while subproof. So I think you write it like this. You just copy this whole thing in. And then at the end here, just like how I did this assignment with substitution, I'm just going to put while this time. And I'm not going to be able to do with substitution. This time I have to do with a nice gross subproof. Your subproof should be, this little bracket here should be lined up with your proof on a lower line. So it should be exactly 4 spaces. For now, I'm just going to put a question mark here. Yeah, so it's not giving me like errors. I'm getting like it doesn't. Now we need to set up our assignments. This you just have to memorize the structure for. It's just once. And if there were any commands underneath here too, then you would have question mark here. Those would get giving me like errors down here once you finish your while. So this can be visualized as like first you do your assignment commands, anything you have up here, then you do your while loop, and then you do any assignment commands you might have down here, and you prove that after doing all of that, then you're guaranteed to have this be true. Now down here, we're going to do, let me show you how you know what you put down here, because this is kind of helpful. If we go to the list of preloaded theorems, there's a lot of these ones I'm sure you've looked at, but you may not have actually opened up this while theorem. And this is how I remember, or at least when I used to have to do the while loops, I would always have to check this. Now I've done this enough across 2 years that I have this memorized. But I recommend looking at this. This might look like nonsense, but basically, this is the structure that we want to create with our setup here. Notice I have Q at the top, and then I have this is my whole while loop, right? Then I have my while B do C. So that's just this part inside, right? My B, my loop condition, is this guy here. And my C, my commands, are these guys here. So it says that after I do this while loop, I'm supposed to end up with not B and Q. Right, that's what I should end up with at the bottom down here. Now, again, B is just our loop condition, so we can replace that. And Q is your invariant. That's why I labeled the invariant as Q up here before, just so you can pattern match it with this rule here. Now we're only taking the bottom of this rule. This symbol is kind of like the implication error. It basically means like if you have this, then you have this. what this rule says is that if you can prove that this is true, then you can say this is true. And that's why we structure our while loops weirdly like this, because this is the only rule that we have that lets us get rid of while loops. We don't actually have any other theorems that break apart a while loop, aside from this one, which breaks it up into just a rule talking about normal commands. And normal commands we can just do using our substitution rules. So our goal is to actually, this whole B and Q, do the commands, end up with Q, that's what goes inside this subproof here. So again, after the while loop, we should end up with our not B and Q down here. And then we just prove that that implies what we want to end up with. Don't forget you're allowed to use implication literally anywhere in the while loops. So I can use implication on whatever steps I want up here. I can use implication anywhere in here, and I can use implication anywhere down here. I'm just going to quickly check if there's any questions. Yeah, thank you. Okay. So now I'm going to get the rest of this set up. So inside of here should be my loop condition, right? My B and Q. And then I need to imply that I end up with just Q. Now I still have to add, I don't have any commands to add down here, so that's good. I still have to add my commands in here. So I'm going to quickly enter down a bit. We are going to probably just copy this exact line. So I need one for this command. And then I need one for this command. So start with my invariant, do this command, do this command. I always work bottom up from these. So you I would start at the very bottom, do your substitution immediately, do the other substitution immediately. Now see what rules you can use to prove that this part up here implies whatever you end up with here. So now let's talk about what our actual invariant should be, since I think the rest of this should be working. If I just quickly check. Yeah, notice it's actually, okay, let me change this. So let me make this something else, that P, something random. Oh, apparently it doesn't mind that. Okay, let's make this, let's just delete that. Yeah, see it says, like, could not justify the step. You should always check this to make sure that your while loop proof is actually valid. It basically tells you if you have the right thing at the top and the right thing at the bottom here, in addition to having the right thing up here and the right thing here, like before and after the actual while with subproof. It checks all that to make sure your setup is good. So just make sure that, like, is this error here isn't here. Make sure it only says found while with no justify error underneath, just to make sure you have the right setup before you start wasting time proving it. So if I put this back in, oops. Now we should be good. So I'm going to start proving this. So I still need to figure out what my actual invariant is going to be. So for this, you're really just going to look again at what is the strongest mathematical property you have that holds at any point in this. A big thing I'd be noticing is maybe I can make some expression about I, because I and n change at the exact same rate, right? So if we have normally that by the end, well, let's see, what can we say at the beginning? At the beginning, this is true, right? At the end, we have that this is true. Underscore 0, yeah. Right, now what I'm noticing is that I starts at 0. So technically we have this at the beginning, right? And if you think about that I is going to keep increasing until it reaches m, well then really it seems like we kind of have this being true at any point in the loop, right? Initially, right, I is 0, so n is equal to 0 plus its initial value. That holds at the beginning state. And then during the loop, every time you're going to add 1 to I, add 1 to n. So you're adding 1 to both sides of this equation, and the whole thing stays true. Finally, at the end, right, when the loop breaks, the loop breaking means that I had to equal m, which means that this has to be true now. So that's the process by which I would be thinking to find the invariant you need to use. You want to think about, like, okay, what can you mathematically ration about with the different equations and commands going on in this while loop? What can you say is always true? Let's see if I got any. Okay, that was a different thing. Okay. And then you want to think, like, okay, is that easy enough to prove from top to bottom here? Does it help me prove the bottom, right? Once those are true, that means you typically have a strong enough one. And then you also need to be able to do this, right? It's really just a matter of the more you include in the invariant, the harder this direction is, right? The harder this part is. And usually the harder, no, sorry, yeah, it's just the more you include, the harder this is. The less you include, the harder this direction is. And typically, usually when I do, like, the more complicated while loops, I have something I start with an invariant I think is good, and then I end up doing this section, and I realize I need a little bit more in my invariant to finish this off. Like maybe I'm really close to having my top equal my bottom. And I'm like, okay, I got to add one little thing in. So I got to have to revise my proofs on the top and bottom just to get this fully working. And that's okay. You don't have to get the perfect invariant first try. Sometimes you start working and realize you need to add a little bit more to it, and that's okay. You kind of realize as you're proving it, like, oh, right, of course, there was this other property that's always true that I forgot about. But for now, we're going to start with that immediate mathematical property that I should always be equal to I plus, or the n should always be equal to I plus its initial value. So that's going to be my invariant. And I'm just going to replace Q everywhere with that. Just checking again for questions. I'm actually, okay, I assume you guys will let me know. One of the other academic managers will let me know if there's someone's got questions, right? I don't really need to keep checking that.
Yep.
All right. Okay, so we'll start with doing this direction. I would usually just go do this, do this. This is typically the easiest direction. Almost always this comes as a direct result of just turning this into an equivalence, right? You do definition of not equals, double negation, you get I equals M from this. And you can just do a replacement to replace I with M. Like I can already see how this one is a very quick proof. Typically, this is your easiest one. I very rarely have found a while loop where this isn't just a, do this and have a very trivial replacement solution at the bottom. Especially for the midterm, I wouldn't expect him to give you guys too difficult of a while loop. So I'm going to start with this at the top then. I may need to do some rules, so I'm just going to have that set up. Okay, so start for both the top and for down here. I always just start really whenever you have commands. I pretty much just start on the bottom, apply those commands immediately, and then work with what I have from there. So in this case, I start with this. I'm going to set I equal to 0 and make sure that goes through. Yep, that was valid. And now just to get to here, that should just be identity of plus. And there we go. That wasn't a very difficult precondition proof at all. Now we'll go do this one. So I'm going to run my commands. So I replace n with n plus 1. Then I'll copy this up here and replace all instances of I with I plus 1. There we go. Now we need to prove that this implies this. So we can start by almost always you're just going to weakening out the loop condition. It's not typically very useful. Having just like an I less than M or having like an I greater than M or an I not equal M type thing is not very helpful most of the time. So I'm just going to get rid of it right off the bat. Nice. Now all it's looking like I have to do, this should just be a cancellation of addition, right? I have a plus 1 on both sides. I think I can just get rid of that. Yeah, cool. So that was also pretty fine. So we've done this direction, we've done this part, we've done this part. Now we just have this last part to do. So why am I forgetting how this works? Definition of not equal. I'm just going to do this in one step to save us some time. So that should just give me I equal M. And then we just have to do weakening to get rid of I equals M. Oh, I forgot to do the replacement. One sec. Okay, that will come in a second. First, I forgot, we have to do, right, we have I equals M here. We want to swap out our I for an M down here so that we can weakening to get our final goal. So we're just going to do abbreviated replacement, substitution. Right, so as long as you have I equals M, you can do abbreviated replacement substitution to replace this anywhere else in your expression over here on the right. And we're done. So any questions about that? Would you give a while loop with sequences? Okay, he said today you'd have the invariant in midterm too. That's good. That's good. Yeah, there definitely could be one with sequences. Again, the big thing I recommend for those, like I think it's an important step that makes while loop so much easier. You want to really like look at the while loop and make sure you understand what it's doing. Like even for sequences, you should kind of envision an array of items and think about what it would do to those items. Sometimes just run it. Like if it's really confusing to look at, just run it on a set of test items and think about like, okay, what's happening to his list? Is it like strips items off, puts them into other lists? Just make sure you understand the loop before you start to run it, or before you start to do your proof. Because then when you're stuck on, okay, what invariants are even true, or like, oh, why does this even imply this? You can start to rationalize about the loop and be like, oh, of course, this is the reason why the invariant holds every time you run the commands. And that gives you a bit of a hint for what to do with this step. I hope that makes sense. Okay, if there's no questions about that, I'm just going to move on to one of the other questions then. I guess I'll also post the solution. Okay, if there's any questions about that one, then I'll quickly come back to that. But for now, I'm gonna move on. Okay, anyone know what we should do? What should we do next? I kind of opened a lot of these already, didn't I? Okay, I'm gonna close 6.6. There was homework 17. Yeah, there's homework 17, cell 8. This question, which I actually haven't done before. Yeah, okay, so a lot of people want this. Okay, yeah, okay, so this should be fun. I literally don't know. I haven't done this before, so let's have a good time. Okay, it seems that this is our definition of univalence we have. We only have this one. It doesn't give us a whole lot to work with. Let me actually read the cell. Crazy idea. Okay, let's duplicate this and get a theorem list open as well, just so I can see what we have here. Not a whole lot. And this is what we need, yeah. Okay. Here you may need distributivity of or over for all or witness. Okay. Well, I'll get to that, or I'll think about that more when I come to it. But for now, there's nothing more to do with univalent R than just immediately apply this definition. Was that what it was? Yeah, okay. Now, I think what makes the most sense here, because I need to create for alls, right? Somehow I need to get for alls out of this. I'm probably just going to have to do relation inclusion, right? This is just going to be an immediate relation inclusion. I have my subset here. If it was equivalence, I would do relation extensionality instead. But yeah, these are my only ways to suddenly produce some for alls. So that's going to be the plan. So let's quickly hop back over to relation inclusion and just copy this definition. Ooh. Okay, so this is my R, and then the identity is my S. Oops. Okay, that worked, cool. And now we got a few more. There's some immediate theorems we can apply before I have to think very much. So don't worry about these names, by the way. You can rename these very easily, like implicitly between two steps. So just imagine, like I'm gonna worry about renaming these later. So I just want to get them into a form that looks pretty similar, and then I'll figure that out. So we're just gonna do relation composition. Just gonna grab that as well. So we got a whole exists implies now. It's gonna be interesting. That should be R converse and then just R. I also need to change my variable names. Okay, that worked, cool. What is the theorem for the identity even? What is it called? Identity relation, okay. Or there's also relationship via I, yeah, sure. Which just means I equals Y. The identity is just a relation that maps every item to itself. So if there's a relation for two items through I, it means that these two are just the exact same item. So it's already looking kind of similar. At this point, maybe it'd be a good time. I don't really want to have to work with these ugly variable names. So at this point, it might be a good time to just make a copy of this up here that has the nice names that I want. Right? I don't only want to have to type B1, B2 each time. So if I do that, these are already looking pretty similar. I'll make that X and Y as well. It's just I have to swap this. Okay, and I'll make this a B. And once I swap this converse around, we're almost done, except it's weird. We have an exists instead of a for all. Huh, that's pretty strange. What? Okay, so relation converse is just going to make that be an X. Wait, why does it say, how does it say this is a cycle? Oh, wait. Oh, yeah, it's telling me this is a cycle, I think, because these are the exact same. I'm just going to make this like a symmetry of, you can make filler steps like this. I'm going to delete this when I'm done. Yeah, okay. Wait, okay. Also, notably, this right now is inside this. Okay, we got to look at our brackets. I'm actually going to take off these brackets to make this a little more clear. Right? Our brackets are a little bit different right now. That doesn't mean brackets. Yeah, so it didn't mind the change I just made with the brackets. Right now, the for all y contains all of this together as one thing. In this case, it's the hang on, no. For all b also contains all of this, right? No, yeah, sorry, yeah. It's the exists is implying this right now. In this case, all of these are inside of the for all. So yeah, we're gonna do this a little differently. Okay, so we are going to. I want this into a for all. The best way I know how to do that is to get a negation on this, and I can actually get a negation on this very quickly if I use material implication, right? That's the one that says implication, like P implies Q is equal to not P or Q. So I'm just going to do that. I'm going to do material implication. Should let me put a negation on that and get an or over here. There we go. And then we're just going to do generalized De Morgan. Yep. Oh, wait, I forgot to actually do it. Which will basically bring the not into here instead. Yeah. And that seems to be good. Now we're going to do the theorem he mentioned at the top here, distributivity of or over for all. Bring this guy inside. Okay, that seemed to work. And now this is just another material implication, and I think we should have exactly what we want to end up with. Cool, right? This turns into, I have not P or Q equals P implies Q. I'll just put my brackets on to keep that a little bit consistent. And then, yeah, I mean, you could technically delete the step if you wanted. I'm pretty sure the whole proof would still work, but I'm going to keep it, because why not? I think what I'll do is I'll put a comment on this. Unnecessary. How do you spell necessary? Unnecessary step for renaming variables, because I think it looks better. Very cool. Okay. And I'm just going to pop that in the chat. Are there any questions about that? I can go explain any little part of that in more detail if anyone wants. Or if we think that made sense, we can move on.
Jacob.
Yes.
I mean, just for people like to see another solution, I'm pretty sure you can just your last few steps after the relation converse, I'm pretty sure that's just witness afterwards.
Oh, because he does say that. Yeah, he says you could use either of these. To me, I kind of saw this vision pretty quickly, and it made sense. I don't.
Yeah.
Okay, so let me. What is
No,
witness
definitely.
again? Oh, okay. Oh, that's interesting. What's my R? Oh, I have no R. Right.
I would just
Okay.
show it in case because it is a
Yeah. No,
it is
that's
a
a good
big
point. Yeah. Oh, is
it
it
skips
literally just this?
everything after that. Yeah,
Yeah.
basically.
Wait, that's crazy. Okay. Yeah. Okay. Wow, that's a convenient theorem. Nice. Yeah, I'll put that one in here too. I'm just going through whatever people ask about. If multiple people agree they want to see something, then I'm giving that top priority. Otherwise, I'm kind of just choosing arbitrarily. If someone posts a cell that you want answered, maybe just react with a thumbs up. If I see enough reactions, then I know I should prioritize that one. Okay, so because enough people said they wanted this one. What is 8.2? Do I have that open? I have 8.2. Cell 17 is not a. Oh, this is not your 8.2. Sorry, this is a different 8.2. All good. Is this the, yeah, this is real 8.2, I think. Okay, cell 17. Oh yeah, someone else, or maybe you asked about that one earlier. Let me see. 8.2, cell 17. Oh, okay, no, that was you, yeah. Okay, yeah, we could do that one next. Yep, that seems fine to me. And then we'll look at assignment 2.1 after that, I think. That should be good. Okay. So, we'll start with this to the top. Is this a relation extensionality one? First, I have to take a look at the. Yeah, okay, so it looks like we have some good theorems for working with this term as long as we have it in a relation, and we have equivalence here. So we are going to do a using relation extensionality. And then, you can just pop this one on the bottom. Okay. So always check to make sure there's no using error. Like if I just did this completely wrong, then I would have a, okay, it doesn't even like that type, right? Because A is a set. Let's try that. Right, then it's going to tell me you cannot justify this using application, so make sure that's always correct. Or make sure that isn't written there, or you've done something wrong. Okay, now that my initial setup is correct, I am just going to do whatever operations I can on these. Like there's a bunch of simple, obvious steps. The only thing I can really do with an expression like this is use this theorem that simplifies it into terms that are much easier to work with, right? So that'll be, what was that called? Relationship via domain restriction. Perfect. Okay. And then we'll also copy this one down here. This is going to be relation composition, which I need to get the theorem for. Relation composition gives me this massive gross exists. So it exists through IDA and exists in. Okay. Cool. So those are all good. And now I can still do one more. I can do relationship via ID if I have a, yeah, okay. So we'll do relationship via ID. So that's going to be, okay, wait, there's two options for this? What is the difference? Oh, it just swaps which one you decide to say is an element of S, right? But this, yeah, this is identical, but you can choose, yeah, you can choose which element you're saying is part of S. Interesting. Why? Okay. In this case, I want to choose X to be the element of A because that matches what I have up here. So I want the first element to be part. So I want the second one. Yeah, okay, I'm going to want this one then. So we'll just copy that. And I have B instead of X, and it should be A. And is that going to work? Okay, cool. Now, it's really important to note what this syntax means. This happens for a lot of operators, but when you see this syntax where it's like term, operator, term, like there's not really like this term is applied to two operators, right? This isn't saying that B being equal to X. It's not saying the Boolean result of this is an element of A. It's really saying this. And that wasn't super clear to me when I first saw that theorem. I got really confused about what identity was, just that it wasn't clear to me I could separate it like this. And you'll see that no matter which way I put this, the like autograder like it doesn't even notice a change. Like it says these are just implicitly identical. So you can just swap these two notations out as much as you want without any theorem needed. They're just implicitly the same. So that is very helpful to know, especially because that lets us immediately 1-point rule this and be done, I think. So we're just going to do a little trading for E. Let me do this properly. Trading for E is just going to put our equality in the range over here instead. And then that should just be a 1-point rule for exists, and we are done. Right. So as soon as you see you have a really inequality inside of an exist or a for all, as soon as you see you have an equality inside of an exists, you should just be trying to 1-point rule it out, like right away. Especially if you have something on top that doesn't have an exists. And then so I'm just gonna paste that one in. Okay, and I think we'll go look at the assignment 2.1 questions now. So cell 14 is this one. I feel like someone asked maybe something else about it too. I can't remember though. So 18, yeah. Okay, yeah, we'll try to go through both of these. I haven't done these before, so good luck to me. Okay, it would make the most sense that we start off by okay, there's kind of two options here actually. This is kind of interesting. If you wanted to be super lazy and just like have this as an assumption to get to use this property right away, you could technically do this. You could do assuming like just this whole thing as 1. Right? And then I could just try to prove that this equals this, Like I could do that if I wanted to. I think what I'm going to do instead is just separate these anyways, like a sane person. That also is an option. And now they're two separate assumptions, because maybe I want to be able to use specifically univalent F or specifically X in domain of F. Like maybe I'm going to need one of those specifically. I don't really have any theorems here that are helpful, except I do have some univalent properties. It's good to know. I have this one, especially. So we'll keep that in mind. Okay, I'm going to need to do a bit of a check on just what theorems we even have available here. Okay, we need theorems to work with this. Otherwise, I have no idea where to start with this. So I'm just going to Control F and search. Okay, 14 theorems. Or no, a lot of, okay. We have this one that breaks it up into an exists and a relation. A relation is nice, I think, because that could help me work with this univalent definition. What do I have for the curly brackets? What even is this? Wait. This is a set, right? Wait, what does this notation even mean? Hang on. This is a fascinating question. Yeah, this is it's a singleton set, is it not? It's a set of just one item. Maybe I should actually understand what this question means. Sometimes for the relational stuff, like I feel like when this course started to get more complicated, I just kind of started ignoring what some of these actually meant, which is a bad idea. We're going to try one thing right off the bat, though. We are going to try to use that relational image. Here, where is that? I'm going to try to use this right off the bat, so I actually have a relation, though, because I'm realizing that might make something apparent with this theorem here. So let's start with that. My R is actually F. My set A is, it's this like singleton set that just contains X. And this should obviously be true. Oh, wait, but this is just an exists. Okay, so this needs to be a new variable. I think this is going to yell at me right now. We're just going to, I'll need to make this something new. We're going to go with Z for now. You can't, like, because you already have an exists here, your new exists variable that you make can't be the same as another relevant variable in your expression. That's not okay. So I'm going to have to give this guy a different name. we'll actually go with E. We're going to go with E for element, and I think that should be good. So why is it yelling at me? Well, first off, we're going to give it a theorem, but that shouldn't be enough for it to yell at me right now. Oh, because it's saying, oh, okay, my bad. It's talking about if Y is an element of this, then you can say this. So this is me not understanding types. I can't say that like a set is equal to a Boolean. So I need to go down here and use, set extensionality. Or what am I doing? My brain fried. And now I can say, I've got, okay, if Y is an element of this, then this should be true, and that should be equal to Y being an element. Now we're working with actual Booleans. Yeah, now it's not going to mind that. Let me actually write the theorem here and make sure this is even working. Cool. Okay. So that was a good start. Now let's see if we can break apart. If this is a singleton set, meaning this is a set literally just containing this, we should be able to say Y being an element of this set means they're equal, which would let us use this theorem. So let's try to see what we have for singleton sets again. I'm just going to search like singleton. Yeah, singleton set membership is this here, right? If this is a set literally just containing this one item, then obviously if X is an element, they have to be the same thing. So we're just going to quickly do singleton set membership to get that these are in fact the same. In fact, I'll format it like the one up here. So we'll put the equals on the other side. Okay. Right now I can probably use this. So let's see, I could just right off the bat use partial function application with, and now I put in my assumptions from earlier. Let's give these guys names. So this is assumption A and assumption B with assumption A and assumption B. And that should let me say these two are equivalent. Yeah, and that worked. I think if I tried to give it with two widths, yeah, that would not work. So you just have to do and like that. I feel like there was maybe another way to do this, like another keyword for it, but I can't remember. This is just what I remember. When you have like a theorem, if you had this whole thing as an assumption, right, you could just feed that. If I just had this as my assumption, the whole thing, then I could just feed it assumption A, and it would be cool with that, right? Like, the heck did I do here? Oh, I get that ticked off. Like, so that would work fine, right? Feed it this whole thing, right? This is a common width setup that you should be used to right now. Being able to, you see that this function or this theorem wants you to provide it this, and then you'll get to use this equivalence as a theorem. So I'm giving my assumption that says exactly this, right? That's what my assumption is. It's a little weirder when you kind of have two assumptions you want to combine because your theorem needs multiple things added together before you get this equality. But yeah, you just have to know about that and keyword. So with assumption A and assumption B. Okay, now I got to figure out how are we creating this nonsense. Oh, wait, I know how we're doing this. Okay, because once again, singleton set membership, right, is just going to say E equals X. Yep. And then that should just be 1 point rule again. 1 point rule for E. Right, if there exists some E where this is true, and that E happens to actually be equal to X, by the way, so we can just get rid of the exists entirely. Yeah. I imagine either just finding the right theorems to start with working with this, or just this syntax. Those are probably the pain points of this question. So any questions about that then? And then I can look at 18 as well. Okay, I got someone seconded this one. Okay. What was this? Last cell of this. Oh my goodness, what am I looking at? Yeah, we'll try that one. It looks fun. Okay. I'm gonna see if I can get 18 out of the way, and then we'll give that a try. I don't think this looks that bad. Okay. Oh. Wait, isn't this funny? Wait, hang on. Am I about to cook? Wait. Okay, wait. Give me one sec. No, okay, hang on. What I was about to do is silly. Okay, wait, how do we want to actually break this apart? Hang on, wait. This might be the first time I'm staring at a question lost on how to start. Do we have membership? Okay, what is membership in DOM? One sec. There was a membership in DOM. Yeah, it's this one. Okay, so we start with doing that theorem. I just forgot this theorem existed. Okay, this isn't. Yeah, this still seems like a fine question so far. Okay. Yeah, so there exists some y. And yeah, now I can start breaking this apart. Okay, this is what I was hoping for. I wanted to get, whenever you have the semicolon, I knew I needed to get like a relation somehow out of this. I just didn't know what the theorem was. Okay. Membership in DOM. Cool. And then we'll do relation composition, which is going to give us another exists. So boy. Okay. Exists some. Oh wait, hang on. Sorry, no, that should be the same variable, but it's x and a y need to be replaced over here. Okay, cool. And then let's expand this one out down here too, right? So yeah, so pretty much always want to start top and bottom and just start expanding them out. Like once I get into this, right? This is a simplified enough term. I've expanded it into some a pretty basic definition. Now I should be looking at this one going, okay, let me expand this into something similar. So we're going to do another membership in domain and try to get some more exists out of this because we have two, membership in DOM instances here. So this was the rule, and I just make that R. And then I can also replace this one actually. I'm going to need a different exists this time though. So we're going to go with B because it's the same variable I had here. We're going to go with B. Which means, what is the exist? No, what was it before? Y. Okay, so this should be like that. And then this should actually be Y. Oops, I don't know how I got down there. And then that should become S. Oop, I don't know, that got deleted in a freak accident. Okay, so that was good. Okay, now let's just make sure our variables actually make sense here. Okay, I don't like this is in the range either, so I'm gonna bring that out. I want to start making these look as similar as possible and realize, figure out what the obstacle is for that. So, okay, let me think. Wait, no, sorry, this is just trading. What am I doing? Trading for E should just give me that. Okay. I can get this looking very similar if I just do this. If I just distributivity of and over exists, right? Then I get this in here. And these are already looking really similar purely because this basically is this. Oh, not quite actually. This variable should be swapped, but that's okay. Now that I know that, I'm just going to swap my variable names, right? I can just do this. There's no reason that can't be B. And then we'll swap all of these. That is totally allowed, right? I can just, these are just new variables I made up, right? The exists, it doesn't matter. They're just variables. So, okay. Oh, and then this order isn't too bad. There's a theorem to swap the order of these two, so that's okay. So I'll do that soon. The current conundrum is what do we do about this? I could, if I was doing implication, then I'd be able to weakening this out, right? I could say, oh, this and this implies just this guy. But when I'm going this way, it might not be as easy. So one option would be I could kind of weakening parts of this out. Probably I could do that. Okay, we're actually going to do this a little differently, I think, because I kind of want to. Okay, I think I have an idea. I'm going back to here because this, I'm going to have to weakening this, and this is an easier, it's easier to get this out. Yeah, I got a plan. Okay. I'm going to delete that step. We're actually going to start to make a subproof in the middle here. A mutual implication subproof. So we're going to start making a subproof. Line up your bracket here with your text, just like when you're making your while loop setup. So it should be, 4 spaces. You just tab over some arbitrary amount of lines and then start when you're trying to figure out what to start here. We're going to do a using mutual implication. There may be a better way to do this, but I don't think it's always important to find the exact optimal way to do it, especially not on a test. I'm seeing this as possible, so I'm just going to do it. So you normally, like when you're doing a mutual implication subproof, you can like say, subproof for and start to declare what you're actually typing, but that's a time waster. What I like to do typically is just toss one side on the top, put an implication, right? And then toss another side on the bottom, and then go make your other subproof. Now you can toss this part on top. Do your implication. And now I will just toss this on the bottom. Now, always before you start doing a subproof, check to make sure. Oh, it's actually saying right now, could not justify this using application. Right, okay, fun quirk of mutual implication. I often use the single equal, or like the double equals for fun in most of my proofs, even though he usually tells you to use triple equals. For mutual implication subproofs, you have to put triple equals on them. And I forget this every time until I see that error, and then I remember to put it on. So now that using error is gone, I verify this is a valid setup, which means if I can prove this and I can prove this, it will let me, say that these two are equivalent, and I'll be done the proof. So here's what we're going to do. We're going to start with this. We are just going to immediately do weakening in this direction. Sorry, that's not the way I want to do that. Sorry, this is actually the wrong one. Sorry. Yeah, this way is going to be different. This way, we're going to do this. We're going to do item potency of to get a duplicate. Okay, we're going to get that. So that's all good. Now what we're going to do is we should be able to get these two to be an equivalent form, right? That we can do. And then we are going to try to reduce this down to this guy. So let's start with the left side, because we already kind of saw that this was possible. We did it earlier. So we're going to start with trying to do this, get these two to be equivalent. Okay. So what I need to do then is, first of all, my variable may still need to change here. I'm not sure yet. I think, okay, here's the plan. This term is completely unrelated to B. So we're going to try to take it out, actually. So we are going to do this. We're going to do, it's interchange of dummies, okay? This is the theorem I was mentioning that just lets you swap these two terms. Also, I need these to start being equivalence rules, and I need to do this better. Okay. So that worked. Now what I want to do is get the X. So like I'm saying, this term clearly has no B in it, so I want to just get it out of B. I want it completely out. So now we're going to do distributivity of and over exists. This only works as long as this term you're taking out does not contain any references to B. Okay. There we go. So I can just take it out of my exists, my B exists, because it doesn't have any B's in it. Now what I can do is some weakening with a lot of monotonicity. What I want to do now is go from here to here with weakening, because then I'll have this on my left side. So I want to weakening this out, but that's going to require some monotonicity. So first, our whole term is something and something. So there's definitely going to be a monotonicity of and. Now that I've gone inside the and operator, I got to tell it why this implies this. And that should actually be, I think there's a theorem for it. This one's, there's body weakening for exists. Yeah, that's a helpful theorem to speed up the, like, otherwise you would need like monotonicity. You could do this way too. You could do monotonicity of exists to work your way inside the exists, and then we do monotonicity, or sorry, and then we do weakening. I think that would also work. Yeah, see, that's also allowed. It's up to you which one you find is more intuitive. I might actually just leave it at this, but yeah, there is that like body weakening of exists to speed that up a bit. There we go. Again, if anyone has questions about anything like this, feel free to just drop it in chat, and the other academic managers will stop me, and we can go through it. Otherwise, I'm just going to keep going, and I'm going to assume this makes sense to everyone. So yes, if you have questions, please ask them. Now I just need to get these right, the right side here to match. So that is just going to be a, first off, it's definitely going to be an interchange of dummies. All right, we got to do that. And now this should just be distributivity of and over exists. Yeah, so we proved the one direction, right? I tossed this into my exists B, and we're good. Now we just got to do this way. This way, again, should be a fair bit easier because we just weakening off the left side. So weakening, kapow, gone. Okay, the only thing left to do is probably 2 steps, I think. Both going to be exists. We just need to do or what am I doing? Wait. Oh yeah, literally, yeah. Interchange of. Oops, not ready for that yet. I need to do distributivity of and over exists. So toss this guy inside. I have done it on the wrong sides, so well played to me. That should be on the bottom. Okay. Now we can do interchange of dummies to swap those variables around, and we should be set. And yeah, so that's that proof. So again, I don't know if there's like there might be some easier way to do it, but like I think once you can recognize the vision that, you know, you can, if you create some more, you can weaken the inside to get this guy here, and if you're going bottom to top, then you can immediately weaken this off and show these two are the same. Like, because I had that idea, I just decided to stick to it. Sometimes the proof will be kind of gross, even if it looks like your 2 sides are really close. But again, if you have a strategy like if you're comfortable with working with implication or mutual implication like this, I think this is totally fine. Sometimes I find stupid like 1 or 2 liners for these, but it's honestly, I don't know if it's even worth mastering those over just being comfortable with doing this. So yeah, I'm just gonna drop this in the chat. Would this 2.1 question be the level of difficulty for midterm 2? Because I don't know if you would know how to make a subproof. You should know how to make a mutual implication subproof, I think. I think that avoiding learning this structure is harmful in the long run. There were definitely assignment questions at the very least that I had to do this for. I don't really remember if I needed it for a midterm question, but I think it's a useful thing to know. And I think that once you have done it once or twice, I don't think it's that bad. It's just that initial barrier of trying to set it up for the first time that always seems very unappealing. Okay. Could you explain the monotonicity parts? Okay. So if we come back to this step here, right? The idea was, we know from weakening that this implies this, right? Weakening says that A and B implies just A, right? If you have 2 things, well, yeah, it implies just the one of them is definitely true. Then if you have 2 things, if these 2 things are true, then obviously you just have you have this one's true. It's just kind of simplifying your argument. That's weakening. So what I'm doing here is just because with equivalence rules, if I had a theorem saying this is equivalent to this, then I can just swap them out without any need for any monotonicity at all. But just because this implies this doesn't mean the whole statement implies this whole other statement. You need monotonicity to justify why the whole line implies this whole line down here. So you start by looking at the outermost operator. This whole line can be seen as something, and something else. So and is like our outermost operator here. So we start with monotonicity of and you can visualize that as letting you work inside of the argument you want to get to, right? Our goal is to get to here, okay? Or to get to here. So we go monotonicity of and to get inside of this. Then in here, we do monotonicity of E to get inside of the exists and say, oh, well, if you have this implies this, then an exists containing it implies an exists containing it. And then finally, now that we've worked our way inside of here, now we can use our weakening statement to say that this implies this. And with this whole thing combined in that order, we'll let you say the whole line implies the whole line. So that's the idea. I hope that makes sense. Awesome. Okay. Okay, so I think the next one was I had a few people wanted to do. Let me see here.
Jacob, before you move on, do you mind if I shared my one solution? I actually found it from last year, or not last year, 2 years ago.
Oh,
when
like
I
a
did it.
solution for this one here?
Basically, to get rid of the subproof, basically. I do agree that you should completely know that, because honestly, that has saved me too sometimes. If I forget certain theorems, just use a subproof.
Yeah, because I feel like it's like usually the simpler solutions are knowing some specific quirk that isn't always helpful for every question. But like the mutual implication strategy is just a fine thing to resort to when you can see that like at least one direction you can do with weakening, right?
Yeah.
Okay, so what is
Yeah,
like
no.
see like it's always some weird theorem with a with that ends up getting you there immediately. But I think if you can see the vision with the mutual implication, it's fine to do that.
Yeah, no, 100%.
Yeah. But
like
yeah,
just
for anyone
me
who wants a
personally,
simpler solution,
like,
and
yeah.
seeing examples of these is always nice, right? Like it's
It's because like I would just say knowing all the implication, like in my case, like I could see that it looked a lot like implication via and.
Mhm.
And if you just modify the quantifiers in a certain way where you can do body weakening like with the implication, but just slightly modify it and turn it into an and instead of an implication. And
So I just want to make sure I understand this. So you got to Oh, so you actually okay, you almost separate. Okay, hang on. So you were just here.
yeah,
And
the only thing
then
different are those 3 lines there.
Mhm. Okay, because body weakening would say that this implies this, basically.
Yes.
And then you
And
use that to then say that this and this is the same as just this one. Yeah, okay. Yeah. I remember this. Okay. This is similar to another one I posted earlier. Yeah, it's actually interesting that this theorem has been useful so often to avoid mutual implication proofs. It's kind of cool.
yeah, no,
So
I would
actually,
say
I'll
all the
quickly go over a
implication
little bit
theorems are
about
very
this.
useful.
Actually, I don't know how important this is to go through. Okay, maybe I'm going to focus on a different question
Yeah.
now. Okay. Yeah, I'm going to do 7.4 last cell. I think I'll do that next. Okay. So give me one sec, guys. Okay, we're gonna give this one a try. Oh boy. Definition of right residual. So this is the theorem we have to work with right residual. Oh, we have a few others. Okay. But we don't have very many options. No, we really just have these two. Okay. That's almost good. The less theorems you have, the less options you have. So no complaints there. Wait, hang on. Never mind. What is this? Calculate an explicit definition for right residual from that is complete the calculation below and complete the theorem by replacing the question mark appropriately. Wait, he wants us to choose what we want to prove? Oh, what? I don't know what this wants. Huh. Is this in the slides anywhere? Like, does he say what this definition should be? Well, I guess. Wait. Is this not? Oh no, this isn't quite the subset relation. Or hang on, what is? Wait. Oh, I think I know what this is. Okay. Oh wait, sorry. Can we do? Okay, I can take a look at that one. Okay, I think I might know what this is wanting us to do. We're just gonna start with this. Okay, so we're gonna get this out here, right? Obviously, we're gonna start with that. Yeah, I haven't proven it yet. Tough luck. Okay. I think here's my vision. Okay, here's what I would be thinking about this question. I have multiple of these open. Okay. I would be thinking about how this looks very, very similar to relation inclusion, which is not. There we go. I would be thinking this looks very, very similar to relation inclusion. So let's just get that out here. Okay, hang on. Oh, we need one more for all for that. Lovely. Maybe we wouldn't actually. Maybe we wouldn't. Hang on, I'm just gonna copy this for now. But what would I be trying to show? Because I need to generate a set here, right? I can't just. Interesting. Let's just replace this. What does that give me? What a question. Give me 1 sec. Okay, I'm gonna write all this out. Oh, this is such a weird one. Okay, let me delete that for a sec. What are we really working with here? So I imagine what it wants is us to create some kind of like definition for it like this. Maybe like, I don't know, like some like it wants us to maybe make some definition like this by rule. So I would end up with like who knows what in here, right? And proving they're the same. What relation stuff immediately breaks up into a for all or something I can work with? Yeah, there's some union. No, none of these break up into a for all either, though. There's only like maybe it's composition because composition breaks up into an exists. Oh, if I can make it okay. Hang on. Nah, but that's still tough to work with. If I can do something's complement. Do we have relation complement? Is that even yeah, wait, yeah, there is. Okay. If I can combine relation complement and relation composition, I can get an exists that I negate, so I can create a for all out of this. So maybe that's the vision. Yeah, I'm just gonna start trying things. Okay, whatever. Let's just see what we can do. I'm actually gonna start from the bottom with this one. So I've decided we're gonna put I'm gonna call this thing for now Q. All right, it's gonna be called Q. And we're just gonna keep adding stuff to it as we need to. I'm not gonna spend too much time on this. If I'm stuck on this, like I'm just gonna move on. But because this is a bit of a weird one where he's not even giving you a goal, and I'd be surprised if something like this comes up on the midterm. Okay, relation complement should give me that. And then we're going to try to do relation composition. So Q is actually about to become a composition now. So it's actually Q composed with, I need more letters, kind of running out. QRST, we got Q composed with T. Oh yeah. Okay, well, sorry. What I should really be doing is just using the actual letters, right? So let's just do this. Let's just do... Yeah, I should probably stop using placeholders. Oh, oops, I ended up over here. Okay. All right, and then we got, relation, composition. We end up with this here. Oops, I forgot my letters. This guy is just going to be E in the middle here. Okay, cool. Unexpected. Oh, I think it's just yelling at me for this. Okay, let's just make... yeah, I don't think I need this anymore. Okay. And then we'll do a little generalized De Morgan. I'm kind of just filling things in that I think can make this look closer to this, So now, like, I have an L naught around this whole thing instead. I can then do just actual De Morgan, right, to get negation on this or negation on this, which is going to let me then do a mutual implication. And we're looking like we're getting kind of closer. I guess I should have made this A, right? Because I want it to match with the one above. I don't really know what I was thinking. Oh my god, I pushed the wrong arrow key. Okay. Right, so we'll do that. And then we'll do, I think I have this. Okay. And then we do material implication to get this implies this. Now we just need to pick the right term so that these become the same thing. So this S should actually be complement of S. If I make this complement of S everywhere, I can make those identical, right? What a fascinating question. I've never done anything of this type before where you have to like keep modifying what you're actually trying to prove. This is definitely the best way. It makes the most sense though. So then, all right, hang on, I need to enter down a little more. This would be relation converse, and then I'll just do double negation to pop that off immediately because that would give me, Okay, so, or oops, what am I doing? That should give me that now. Nope, did not like that at all. Oh, not converse, complement. Oops. Okay, there we go. And then the last thing to do is just this guy needs to be swapped around, so this should be our converse. So I'll just replace that everywhere too, and then we should be good. Oops, I copied it with a space. Yeah, okay. Let's put that literally everywhere. Now we can swap these guys around. Relation converse. Okay, so that is, I guess, the definition you end up with if you just kind of reverse engineer it, right? Works, I guess. Yeah, I don't know. That's a weird one. I'm not really sure that's exactly how he intended us to do that, but now we have, by kind of reverse engineering, looking at the definition and trying to get something close to it, we found some definition for it at least, so that's kind of cool. So right residual is equal to the complement of R converse composed with S complement. There we go. Okay, 6.3 last cell. You can try this one. Any questions about that? About this one, I guess. Oops, with this one. But again, I don't know if something like this is really going to show up on the midterm. I'd be surprised if it makes you try to like reverse engineer a definition. Oh, I didn't post it. Oops. Should probably do that. Okay. Yeah, we can go through 6.3 last cell. Okay, how even is this? Oh, okay, practice with quantifiers. Okay, so we need to prove this whole thing is equal to false. Okay. Yeah, we're gonna start with this at the top then. So yeah, it says aim to use generalized De Morgan. So in this case, what we're gonna want to do right off the bat is probably a little double negation. There's kind of a few ways to work with this equals false setup, but I'm just going to do the most straightforward one. We're just going to do double negation to produce a not on it. Hang on. Or actually, maybe generalized De Morgan doesn't even work the way I think it does. One sec. Oops, I need the theorem list. Oops, generalized. Yeah, okay, yeah. There's a variant of it where you don't need a not on the exists. So hang on, scrap what I was about to do. We're just going to immediately do a little generalized De Morgan to convert this to a for all. Because that is supposedly what it's saying to do. Or maybe it wants us to do, hang on, I should maybe look at a bit more of this. What do we actually work with here? I should look at it before I just start doing things.
You can start by, like, can you not use definition of the L naught from equivalence? And then you can use generalize De Morgan, right?
I'm trying to think about, like, what is the vision? Once I expand this out, what am I actually doing from there? Just, what is this saying that says there exists some y such that for all x, this is true? What would that y be? Wait, what? How is that possible? Oh, it's false. Oh, we're saying it's not possible. Okay, you're right. Okay, yeah. I actually, have you done this notebook or anything from it? I don't actually know what the general process he wants us to use for this notebook is. Interesting.
Me?
Yeah. I don't immediately know what I would do to prove that this is
No,
not
I've
true.
never seen this before.
Yeah, interesting. Okay. Yeah, I don't know. I'm just gonna generalize. I was thinking the first thing I would do would just be like, generalize De Morgan, negate that, and then maybe negate like the inside here or something. Like that's gonna work, right? But then what do I do from here?
It's
What
by
is the actual-
cases. Oh, he says to use case analysis. Someone in the chat said that you gotta do it by cases.
Oh, I'm actually blind. In this case, a case analysis may be needed.
Yeah.
How? Okay, what are we casing out? So, what? What would you be doing cases of? Okay, so logically this is false because, like, why? Like, I feel like when you're really stuck on what direction to even go, you want to ask yourself, why is a question even false? What's the simplest way we can explain that this is just not true? And I guess if we could prove that its negation is true, that's also an option. The easiest thing to do would definitely be to convert this into two exists, actually. Oh, yeah. Hang on. Okay, one sec. I know. Okay, let me try this again. Take two. If you can get this into two exists, then there are options for sure. Yeah, let's give that a try. Right? Yeah, that worked. Okay. So now, yeah, definition of not equals. We'll just make that, Actually, that's not even necessary. No, we're not even gonna do that. Okay, so if you can prove a statement implies false, that should prove that it's false, right? Yeah. Let me test something real quick. Yeah, hang on, we're just trying something. If I magically have an implication here suddenly, is it just gonna let me like say that's true? No, it doesn't quite let that work. Okay. Because I'm going to be wanting to use an implication. I think, or no, wait. I'm thinking of the wrong thing, right? I want to do a for all almost. I can do this actually. maybe. But that doesn't help what I want to do. I want to like use instantiation somehow to basically give it examples where this is false. Maybe that's not exactly how this works though. Is there a specific X where it's really easy to show this is false? If I just pick X0, then that would... No, but I need a specific Y. What a question. Yeah, I actually don't... I don't know how to... Oh, it's Y equals 0 and Y does not equal 0. If you assume Y equals 0, then you're left with, like... What? X equals 7x, and is that easy to disprove? I'm not sure I'm actually seeing the vision for this question, huh? I think just because I haven't gone through this whole notebook, like, I have no idea what it wants me to do once I actually get to start working with the numbers, you know? So I don't really know what this would look like. I think I might move on from this one, to be honest. Unless someone wants to drop a solution and I can try to explain it in more detail. Yeah, actually, I'll just toss this in here and try to explain this. This is the right thing. Yeah, okay. So let's check this out. Okay, so you generalized to Morgan to get 2 for alls now. And this is nice because you can immediately do a for any, and now you're just trying to prove this. Yeah, okay. And you start to do cases. So why do you need these cases? If you want to say this is true, we're gonna try to prove this is false. So what do we do here? We're just picking a specific example, right? Okay. Yeah, right. If we're proposing this is true for all x, we just need to show any x where it's not true. I'm surprised it's not just a theorem for that, like counterexample or something. It feels like something you have. Is that not a real thing? It feels like this feels like a theorem you have. I'm surprised. Okay. But yeah, so this is just a proof by counterexample. Okay. He's disproving this, right? Which ends up proving the whole statement. Okay. Yeah, you pick some specific x for which is not true, and then E introduce the exists. That makes sense. And then when it is 0, sorry, when it's not 0, now you can do... Wait, oh, you just produce... Fascinating. Definitely would not have thought of this. I was wondering if we needed the not equal 0 for like cancellation of times. Like I was wondering if this was going to be the place somehow. Maybe you can do the same thing with that. Yeah, no, you can't because we don't want multiplication on both sides. Huh. Oh, you know what? You could start with like a 7 not equals 1 like you did before, and then use this to get an x on both sides and kind of create the same thing, I guess. No, but no, but you need the y. You need the y. No. Yeah, I don't know. Huh. I'm gonna move on to a different question now. Why are we allowed to use the backwards implication when it's supposed to be an equivalence proof? Okay, so that's actually a good point. This is good to know. So you'll notice that in both of these proofs, they start with true and then have an imply and then end with something. And this is just considered to be valid. So you're not trying to necessarily prove it's equal to true, okay? You're trying to prove the statement's true, all right? The goal here right now is just to prove this statement. There's a few different ways to do that. If you want to prove some statement P, the easiest way to do that, right, is just to prove that P equals true, right? This is this, or like, P equals true. That's the easiest way to prove P. Another valid option, though, is if you think about it, if we think about the truth table for implication, right? If you have this statement is only true when P is true. Because as soon as P is false, you have this, and this is false, right? True implies false is the only case where implication is false on the truth table. So if you can prove true implies P, that means P also had to be true. So in this case, yeah, you can start with true, do an implication, and then end up with what you wanted to prove, and you've now proved that this has to be true. What I see people do sometimes, which you cannot do, is this, right? Because again, the only case where implication is false is where you get this, which means that if you have true, it doesn't matter what you have up here, right? This implication is always true. That's just how that's how implication works. So this, proving this statement says nothing about P. If you say this, the P could be false, and this would still be true. So that doesn't work. Okay, so bad. Doesn't work. All right. Does that make sense? Awesome. Okay. What is it? What should I do? Figure this out. So 7.4. Well, yeah, I'm gonna need a notebook link for that one, unless I have it open already. Oh, is that what this was? Oh, this was 7.4. Okay, I do have it open. Okay. What is that? Self 14. Oh god. Probably the answer is probably no. This stuff I'm not very good with, actually. Very likely I cannot do that one. Oh my god, my stream is messing up for me. Okay. And then what was the other thing? I feel like I had something else on my list I was gonna do. Oh, there's 22. Oh god. Oh, what is this? Oh, I remember. I feel like I have a vague memory of this one because this was like one of our homeworks or something, or maybe this was our assignment. I don't even remember, but I know I did this question and I hated it because I needed like multiple different subproofs off on the side. Yeah, he's like, oh, you can use some side proofs with continuing. It might be helpful. Oh man, okay. I only have terrible co-options left. We're gonna try to do the other one then. This actually seems less terrible somehow. Okay. Yeah, let's just give this a try. Why not? Start with this. Prove it is a subset.
For the other one, if you don't get to it, I can just give an answer for it or something.
Okay. Yeah, that's probably fine then. Okay, I'm gonna try this. So I assume we're gonna be using a lot of these up here to make this work. For example, we have modal rule right off the bat that we could try to use. So how about we do that? We could do an immediate modal rule and get this. Okay. Now, what do I actually want out of this? I need each of these to be intersected with S, and I need R on the other side again too. What the heck? Okay. Another thing that's very important for these is you should try to put some brackets around these to make sure you actually understand what you're trying to prove. For example, I believe the semicolon bind. No, wait, no. The semicolon bound tighter. So is this what I'm working with right now? Let me just try to put this. Okay, see, that broke it, so it doesn't like that. So I'm going to put the brackets over here now. Oops, I just did the sticky keys. I'm going to put the brackets over here now and confirm that's what I'm looking at. Okay, which means that this isn't even technically necessary. Like, it could just, yeah, the statement could just be written like that. Okay, that's why I tried the other way first, even though my gut said the semicolon binded tighter. But yeah, putting these brackets on can just be helpful to visualize what you're working with so you don't get confused about what's intersecting with what. So we'll do all that. Okay. So, do I have theorems for intersection like this? We only have this on one side. Huh. Yeah, these are all, it's interesting. There's no, we don't have symmetry of this, do we? Is there any kind of symmetry property we have here? I don't think so. We have associativity with the brackets, but that's about it. Yeah. Okay, so we don't have a whole lot to work with. What theorems do we have in this notebook? Really nothing aside from, yeah, it doesn't look like we have like basic set theory, but otherwise we're really just working with what we're provided here. Okay. Okay, well then. I don't think the monotonicity rule is going to be particularly helpful here. Unless I want to use it with, the one case maybe, I don't remember if this is a thing that ever needs to be used. I just want to quickly see this. Technically, because of this, wait, hang on, what even, or oops, it'd be like this. No, yeah, this would just be the same thing. No, that would not be helpful. Okay, no. Gotta consider all possibilities. Okay. Well, could I ever, maybe we start over here then. Maybe we hop down here. Hang on, how do I want to do this? Control B, okay. Maybe some progress can be made in this direction. Does this look like it matches any of these patterns? Not really. Just to clarify, we're not, or I believe I'm not supposed to be using, wait, am I supposed to be using relation inclusion for this? Like, am I allowed to use these? I wasn't sure. I know there's some theorems where you're not supposed to. Okay, are you allowed? Okay. I hate this all the time because there's some notebooks where he says you're not supposed to use it, and I'm never clear on when those are. Okay, if I'm just allowed to use it, and this is probably not bad, then okay, I'm just gonna, yeah, whatever. Okay. Yeah, relation inclusion. Let's just start doing that. Oops. Okay. This is going to be an absolute monstrosity, huh? Yeah, I don't know why I said this was not going to be bad. This looks horrible. Relation intersection. Cool. Relation composition. Okay. We got Q and R. I gotta fix my variables too. X, Y. Okay. That's about as much as I can expand this one. I can bring this inside because it has no B in it. I'll worry about that later. Now I gotta simplify this one at the bottom. So we'll start doing that. Okay. So this one starts off as an immediate relation composition. I guess I'll just copy this. But in this case, my Q is this monstrosity. And my R is that nonsense. Cool, okay. And then another relation composition. Holy moly. I'm gonna have to make some new variables this time. Wait, no, hang on, I forgot. This is relation union or intersection. I almost forgot, right? The semicolon binds tighter. Can't forget. Okay. Wait, oh, that should be B, right? Yeah, okay. And I gotta do the same thing over here. Y and I can't type. B. Okay, so that all worked. And then now we can separate our relation composition. Oh my goodness, this is disgusting. Okay. So it's S to B this time, and I need another element, so this will be C. Or X to B, I meant. Okay. And then this is the converse. Work. Okay. And then I got to copy a very similar one over here. This time it's from B to Y, so B and Y. And this should be Q converse and S. And then I may need to rename my variables. It's not usually great to have multiple of the same variable in your exists when you start trying to combine them later. But maybe it won't be a problem. Okay. We're almost done. This line has no converse, so I'm going to make sure this one doesn't either. So I'm just going to do a relation converse just to swap these around. So we get B and C. And then over here, we should get C and B. Okay. All right. We got all that out of the way. Oh, I'm only now realizing it says, oh yeah, it says can't justify this using application because I'm not using implication. I just noticed that, which is a good reminder to me that I'm allowed to use implication, which will probably be necessary because this is not an equivalence rule. Okay. So let's see what we have here. This is a term that we have in our exist here. This is kind of a term we have. We have that for Y, yeah. So we could E instantiation to probably get that. This is something we have. And this is something we have for X. This is something we have for X as well. Yeah, okay. So these could both be some instantiations then. So let's start making some changes here. First off, I'm just gonna actually before I even do that duplication, I'm just gonna bring this around to the front because it looks a bit better to me. Because it looks similar to what I have here now. Now I'm gonna make some changes. How do we want to do this? Okay, first off, actually, this should get brought inside, I think. What's the term? Distributivity of and over exists. Yeah, you can bring that in because it has no references to B, right? There we go. Now we're going to need to start doing some expansion and some E instantiation. So let's start to do this. We're going to do some item potencies of to make some duplicates here. So first I want this one. I need a relation through R, my relation through S. In fact, let's just copy this over here. Now I don't have C yet. Right now my C in this case is going to be Y, right? Because I had that and I have that. I'm going to do an instantiation where I replace that Y with this C over here. So that's fine. That'll be the one group. I'm actually just going to put those in brackets to show that's going to become my one exists. For my other exists, right, I'll copy these as well. They'll go in their own pair of brackets. And in this case, my C is going to have to be X, and that works because that's what I have. Yeah, I have this as well, so that should still work. Perfect. So I made a bunch of copies of these guys. Now I'm ready to use E introduction to turn them into exists. So I'm probably not going to need this extra step after all. So this should be E introduction. And I also, or I need, okay, but that only, E introduction only tells me that this step implies this step, but my whole thing is wrapped in a bunch of exists and ands. So first, again, my outermost operator in this case is an exists. The whole thing is wrapped in an exists. So that's going to be monotonicity of exists. Then once I get in here, I still have a lot of ands here, so I want to separate this. I want to separate them. I want to work inside the ands to this term. So that should be with monotonicity of and. Now I'm inside the and trying to say this implies this exists, which is by E introduction. I think I might want me to make some, yeah, it's probably going to want me to do one more step actually. That I forgot about. I need to for E introduction, I need to create some substitutions. So it should be, this should be the case where C equals Y. And now I can replace the C's properly down here. And we'll do the same thing over here with c equals x, and replace these with c. Yes, the substitution step was valid. Okay, it still didn't like this. Oh, I guess the s doesn't actually exist here. Oh, hang on. Wait, let me try this. If I just and the, let's do this at the beginning. I just need to have this, I think, is what its issue is right now. I tried to compare the two lines and I noticed this is the big difference right now. Yeah, I should have that. Oops, I put this in the wrong step. Sorry. I should have it up here. And then I'll get rid of that after. Is that working right now? No, it still doesn't like this. Okay, but once I do this, this should just be monotonicity of exists with weakening. Yeah, so I can at least get this working where I get rid of the s. But now why does it not like this still? Let me actually take a look at oh, I need to copy this. That's what it should be. Okay. What is different about this? That one seems fine. Did I mess this one up? No, c equals x. Yeah, this seems fine. Okay. Should I just try doing one at a time? Nope. Well, that's an interesting one. Monotonicity exists with monotonicity of and. I'm gonna try just making two different variables just to see if this is the issue. No, I'm gonna keep it that way for now anyways, because it can kind of implicitly rename these. See, it doesn't, these two steps are still valid, it just renames them automatically. Yeah, huh. What on earth kind of bug am I experiencing right now? Like, actually. Is it just monotonicity of exists being annoying? This theorem is kind of weird at times. I don't know if it's a quirk of the fact that this theorem like wants a for all statement, but monotonicity like just weirdly doesn't want to work sometimes. Oh, there's different versions of it. Hang on. Do I need like, I don't know, should I just try one of these? Simple body monotonicity? I don't know. No, I didn't change anything. I don't know. Okay, well, I mean, still, as long as everything else seems the same, logically these are equivalent. Like, or logically this does imply this. So I'm not really sure what weird calc check quirk I'm missing. If anyone really wants to know, maybe they can go ask Kyle about it. Or someone has a solution somewhere. I'm not really sure why that's not working, to be honest. But I'm not going to waste any more time on that. Okay, what else do we want to go through? I guess I can scroll up. There was homework 16, cell 18. Okay. Probably gonna be kind of a similar one to one of the, or to one of these. We can give that a try. I'll quickly paste what I had from the last cell. If anyone can figure out why this isn't working, that'd be cool. Oops. Okay. Yeah, we'll take a look at this one. Sorry, give me one sec. Okay. Yeah, we'll start breaking this one up using relation inclusion then. So we get to use implication for this. Use this body monotonicity exists. Is that all I need? No, okay, so that alone doesn't work. Okay, so that with monotonicity of and, with left monotonicity of and. What? What if I just make this regular monotonicity of exists? Okay, so this also works. So it's just this theorem. It's this nonsense that makes it work. What even is this? What?
Yeah, Jacob, I believe it's because there's multiple, like those only apply for one. Like if you were to actually write it with all the brackets, it's kind of like scoping in to, like, I don't know how else to put it. Like the first monotonicity of and gets rid of one of them. The second
Oh,
one
so it's
gets
not about the left. If I just do that, it also works, you're saying. No. What?
Oh, wait. Actually,
Wait, yeah, I thought you were right, but I was like pretty sure that also wasn't how it worked. But no, it actually just specifically needs this, even though this literally has the name monotonicity of and. This feels to me like a bug almost, right? Like, look, it's even saying found left monotonicity of and it still doesn't work. What? Yeah, as soon as I got stuck on this, it was reminding me of when I had some weird quantifier bug. I couldn't remember. I replaced it with some variable. Oh my god, did I? Oh, I feel like I remember what you're talking about. That's actually the dumbest setup ever. Okay. I don't remember that now, unfortunately. So I guess I'm not as cracked as I was last year. I think because last year I must have understood the error and had some weird bypass. This time I don't understand what the problem is at all, to be honest. Huh. Oh well. If we have a solution, we'll just go with that then. I'm actually curious if I even need the other width. What if I just do, left monotonicity of and from the beginning? No, okay. So you really just what a bug. Wow. Okay. Okay. Is monotonicity keyword enabled or no? Very cool. Very, very cool, Cal. Okay. Yeah, maybe someone should ask Cal about this. Maybe I even will. Who knows? That's an interesting one. But like it should be trying both. By the way CalcCheck works, it should be trying both. Yeah, I don't know. Fascinating. Also, like obviously more importantly, it shouldn't matter. Like it's symmetric. Now the new question is, am I able to just do this? Now that's just bizarre. Now that just makes no sense at all. What? Yeah, I don't know. Okay, again, not gonna waste any more time with this, but interesting question. Okay, so I guess I'll just pop this into my new one. Or I'll just dump this as well. Okay. All right, so back to this one. First thing we're going to do, so I don't want to forget that I can use implication, but for now I'm just going to expand it out like I did before. Relation composition. Okay, so we'll replace our relation composition with the classic exists. Make that x and y. That should be q. This should be r intersect s. And then we do relation intersection. Very cool. It's going to give me a using error because I'm not using implication right now, but that's okay. Relation intersection. Is this just the classic like thing you want on both sides? Have fun. I think it is. But I think I know how we do this one. This one doesn't seem bad. Hang on, new strategy. And then kill that. And then do it again, and then kill that. And do I just get the exact same thing or what? Yeah, that's exactly what I want. Okay, I had a feeling. Yeah, I just saved myself some time setting up the exists. Okay, so as you saw, I was able to produce it by just taking two of these and taking a term out of them, right? Which is a bit of a hint for how we're going to solve this. We are going to, we can use implication, right? We get to use the implication arrow. So we're going to do this. We're going to do idempotency of and to get two of these. And then we're just going to do a classic monotonicity weakening setup. Oops. That did not work the way I wanted it to. Now, so what I want to do is I want to say, you know, I can weaken this down to this, and I can weaken this down to this one, you know, by removing this term. So our outermost operator is an and. So monotonicity of and. To make this an implication. Actually, I don't even know if I need another rule here. I might just be able to go directly to where I want to. Monotonicity of and with monotonicity of exists, right? Once monotonicity of and to work my way inside the and. Once I'm in here, monotonicity of exists to work my way inside the exists. Now I should be able to do it with weakening, and that this rule should apply to both sides. And yeah, so that's not too bad. That's definitely a lot better than what we just did, at least. Right, so we had this, we idempotency to get two of it because, you know, we need to reduce it on both of these sides, and then use the monotonicity setup to weaken the inside of the exists. This has been a pretty common setup we've done throughout the day now. So definitely make sure you get some practice with those, but I feel like this comes up a lot when working with these set theory questions. Okay. Right. We got a few more minutes. What else would we like to go through for the last 7? I don't really feel like scrolling up, so repost any questions that I haven't got to yet. I don't even remember what I've done at this point. Oh, sure. Could you possibly like drop the cell so I can just paste that into the exact same setting? Like, or you could just like the notebook and tell me what cell that was. Okay, 7.4, which I have open, right? Is that? No, here we go. 7.4. So 24. Okay. Wait, what? Wait, am I on the right? Wait, that's not a. Is that this one here? This 23? No, you're okay. Oh, I might have like made a cell. Did I make an X? Is this no? Okay, this isn't. I knew there was a notebook where I made an extra cell, but I don't think it was this one. No. Okay. All right. Could you maybe post your whole proof for it? I assume. Yeah. Okay. Thank you. Yeah, I can go through. I can go through that. Wait, how much did I copy? Okay, I copied the whole thing. Okay. All right. No, it doesn't. Okay, it's not quite done yet. Okay. Oh, you just want to see why this isn't. Okay, you want to see specifically the trading and 1 point rule. Okay, sure. So when you have these assumptions inside of an exists, they're very useful because you get to do 1 point rule. If you have an let's just quickly hop out to 1 point rule. 1 point rule is just saying if you're saying there exists some X where this property holds, but the only items you're considering are the items where X is equal to like E, then you can replace X with E. You can just say, oh, the statement holds for E. So if I'm saying there's some, actually, I don't know if I give an example like that. I don't have a good example for that one, actually. I don't have a good analogy, but that's the concept. So let's split this up a little bit. We're just going to do 1 point rule and then substitution down here. So 1 point rule would let us replace this entire exists, right, with just the body of the exists, which is everything after the bullet. So we get all of this. So I take off the bracket, take off all this. I end up with this is my body. And I actually have to put the brackets back on because I have to say I'm substituting in. I'm letting Z equal to B. I'm letting Z represent B. Why are you yelling at me? What did I do wrong? Oh, that should be a Y equals C. I just cut that off. Oops. Never mind. What did I do wrong? What? Wait. Huh? Isn't this exactly what it is down here? Oh, equals C. Got okay. Don't worry about that. Okay. Sorry, I left it equals. Okay, I left the equals C over there. So after you do 1 point rule, you end up with the original body, but now you substitute. You're saying, okay, so you just copy the exact original statement, right? But you're now saying, okay, this Z variable that I had, that represents B. That's B. And then you can just do the substitution to get B in there. So once you get comfortable with the setup, you can combine it into comma substitution, right? To just do this without needing to actually like declare the substitution. You just put B here. In fact, you don't even need the substitution rule. You can just do that. You can actually just ignore the substitution completely and just do that, and that validates, which is kind of neat. So if you actually, you don't need the comma substitution. Does nothing. Calc check does let you implicitly do that. So you can just copy the statement out of the exists as long as you have an equivalence in its range. You just copy the statement out of the exists and just swap the variable out, right? So you're eliminating the actual exists bound variable for this non-exist bound one that you can take out. Oh, how did you know? Oh, that's just because it would. I assume okay. Normally, you'd only have one. Like if you only have one equivalence, well, then it's obvious that you want to use this one. If you're asking how do you know which of these to use, I have no idea. I haven't even looked at the question. I imagine you would maybe work this one up and see. Like, I don't really know. Because we still have this. Actually, hang on. There's 1 point rule for all as well, right? Like, yeah, you would just do 1 point rule for all next. It doesn't actually matter which one you swap out. You're going to do both. So the reason you put it in the range is just because that's what you need for 1 point rule. Purely because 1 point rule needs it in the range. That's how you know to just toss it into the range. Does that make sense? Yeah, the 1 point rule only works if you have an equivalence in your actual exists. It's just a way to, if you have an equivalence in the exists, you can just get rid of the exists. It's just a useful property. So often if you see an equivalence inside of your exists, you should just use training to put it into the range and then 1 point rule right away. Yeah. So to finish this off, you would need to get it into this form, right? Once you have it like this, then using some trading for all, I'll leave that to you guys. Then you can just do 1 point rule again to get it into this last form. Yeah, see that validated? It doesn't even make me change the variables. Like, it doesn't even care that I haven't changed the x to a. You can just implicitly change between x and a and whatever, as long as you don't have another x or another a defined as a real variable, like an unbound to the for all variable, some global variable. Like in this case, like b and c are kind of unbound global variables that are just part of the actual theorem. But x and a aren't, so you can just replace them as you want. In fact, even if my final line is x, even though the actual theorem wants a, like that's still totally valid. Wait. Oh, apparently that's not valid. I actually didn't know that. Oh no, it's just because I didn't replace this one. Yeah, see that it just assumed I renamed it. It doesn't mind. Like it still says calculation matches goal, even though it's a up here. Yes, yeah. When you need to get rid of exists, you're typically looking for a way to get a 1-point rule. Otherwise, you'd have to use e-introduction, and if you don't have implication, then good luck. 7.4, cell 14. Oh boy, is this going to be some monotonicity fun stuff? Let's find out. So I'm just going to make a duplicate, I guess. No, I don't need this anymore. I pasted this already. Actually, wait, no, I might want to compare it to what I did, and this would be easier. So we'll make a new cell below. In fact, and I'll paste your thing here. Yeah, so I mean, it's just yelling at it. Yeah, this is literally the same issue I had, right? I thought I had this figured out. Oh, but you actually got the first one working. And then it's just going from here to here that you can't get to work. Yeah, so this is the same bug that I had. Right, kind of. And I can't fathom what the problem is with it. Monotonicity of exist, work your way inside the exists, perfect. Monotonicity of and, get over here. E-introduction should just work. Truly completely lost on why this would not work.
He has reverse imply signs.
What was that, sorry?
Reverse imply signs. It's supposed to be the other way around.
Oh, true. Wait, yeah. I don't know what I'm saying. Sorry, yeah, that's totally right. Yeah, you can go from the actual term. Hang on. Sorry, I just assumed the direction was correct because of this. Wait. What was happening here? I'm actually curious. I think it's going to hate that I have two different like directions in this. I'm just curious if that will validate or not. Yeah, see, this way validates right now. But then it loses its mind. Like, hey, you have two different arrows in different directions. What are you doing? Yeah, thank you. Yeah. Okay. Oh, we're the one we just did. Yes, of course. I didn't, or you mean 23, right? Like, I know I didn't finish this little part here, but I'll at least post that in complete solution. Okay. I think it's 8:03. We're gonna end the session now, but first, I think Pavlos, you wanted us all to give a little tip for the midterm.
Academic manager can give one piece of advice. Could be for this midterm or just for the exam coming up. Just one thing that helps you get through the course. So I'll go first. One thing that helped me was sort of that we discussed it in midterm 1, but sort of like the part mark strat. So if you want to revise that, I recommend you go back to the midterm 1 YouTube video and we go more in depth with that. But essentially, when I first open the test, the first thing I do is I just fill out every single question. Like, so there's like certain structures for each type of question. For like a while loop, I will fill in like the top part, a bit of the middle with the assignments, and then the ending. Or like there's with the relational algebra stuff, I will fill in if I'm doing a usings proof. So I just fill in like sort of like the keyword things, and then once I've done all that, I will actually pick the question I want to like solve fully. So what that does for me is it sort of gets me thinking about like all the questions, like like they're all in my, so like I laid the foundation for all of them, and then when I go to actually do them, they're sort of already like they're started, so they're just easier to complete. So I recommend just like farming out the part marks like that. And then another thing for just passing the course is the curve is a real thing. So I always like to keep that in the back of my mind, that like even if you're in like the bulk of the distribution, like on Avenue, like when you do your tests, like that whole distribution gets shifted to the right. So like if you're in the middle of that distribution, you're gonna do really good in the course. Like that, the curve is really big. Yeah, that's my tip. So I guess we'll go to the next person.
Nice.
Okay. Why everyone's just quiet? Yeah, I don't have anything much more to add to that. So, yeah. Whenever you get stuck, I suggest just start working top down and bottom up. And honestly, like even if you don't get like the one hint item in the middle, you'll get like 90% of the part marks for that question. And also for while loops, the structure itself is like 40%. So
yeah, I do want to mention for while loops, when I did my midterm too, I couldn't figure out the invariant, but I knew how to do the structure. And so what I did is I just came up with a false invariant that helped me, like, since it was false, I could sort of just make it up and then just fill in the structure for the while loop. And then I was able to fill in every step on the while loop except one, and I got 95 for that notebook. So even if you get, like if you can't figure out the invariant, just being able to fill in most of the structure with like a fake invariant, that can get you like basically enough like for 90 or 95 on that notebook. So yeah, I just recommend if you can't get the invariant, just try something that will just help you fill in the cell with the structure, because one part of that whole question is Cal just wants to see if you can just do the structure. That's basically a fake invariant.
I was gonna ask the same thing. Yeah, what do you mean by a fake invariant?
So a fake invariant is just
like it's not actually invariant.
It's not the invariant. So basically,
I think it's wrong to say the invariant, right? It's not a invariant. You mean like
yeah,
it's
just
not...
like just fill in Q, which is the invariant, with like just any expression you want. Like it can be whatever you want, and then you just want to have Q. Q can be whatever you want, and then just make it so it helps you get to the end of the while loop. Like it's just something that CalcCheck will know is what you think. It's like what you're trying to say the invariant is. So it's just put any expression you want. It might not be true, but it's just something so like the parser can like check if you actually have something you think is the invariant.
Yeah, well, you can look at what kind of expressions would let you prove from the precondition. Yeah, exactly. Something like if you can see something that would let you solve the precondition and solve the postcondition, ideally entirely, that's great. If it's not strong enough to prove the inner part of the while loop, then it is what it is. You still got most of the marks, and you didn't technically choose a fake invariant, most likely. You probably did choose one that holds. It just may not be strong enough to prove the whole loop.
Yeah.
Yeah. But yeah, I would mainly look if you're stuck on trying to figure out like a good property for the whole loop, maybe just focus on what's true at the beginning and true at the end, and just try to make some expression that's true in both those cases, and just start working with that, right?
Yeah.
And because it's true at the beginning and because it's true at the end, you should be able to prove the top and bottom. Like those should both be possible, as long as it is true at the beginning of the loop and is true at the end.
Yeah. Yeah, some pattern matching things I like to keep in the back of my head for the while loop is like, so usually when you get into the middle of the while loop, there's usually a weakenings. That's what I like to remember. So when you're inside the actual subproof, inside the while loop, there's usually a weakenings most of the time. So I just like to keep that in mind. And then when you're at the very bottom of your loop, the post condition, there's usually also weakenings there with like a substitution.
Yeah, remember you're allowed to use implication anywhere in the while loop. Pretty much anywhere in the loop, you can always use implication. So you're going to do a lot of weakening. Not every part of the invariant is useful at every point in time.
Yeah.
Oh, I got rid of my proof. No. Here it is. Just to quickly demonstrate with this one. Oops. Right. As soon as you have your negated loop condition and your invariant here, you should immediately, like, most of the time you're just going to weakening out the negated loop condition. This guy is really only helpful at the end of the loop where it becomes something useful. Most of the time, I not equal m is like a garbage assumption to have. It's not helpful information. And then at the end, once you use this loop condition, you also probably still have to weakening it out as well. Or maybe you might have extra stuff in your invariants that also needs to be weakened out, right? Typically, the weakening isn't as important at the start because you want to like create more info from not having as much. It's the opposite issue. Is it mandatory to use substitution in the last step? Didn't rev it that much. Substitution in what last step? Sorry. Did I do it here? Sorry, Dina, are you talking about this while loop solution, like these last three parts down here? Or a different question? Generically, but like for this part. Oh, I see what you're saying. Like are you always going to be doing substitution like this at the last part of a while loop, you mean? Yeah, most of the time, yeah. Most of the time if you think about it, like in the middle of the loop, you're running a bunch of commands. You don't really know as much about your values, but at the very end of the loop, you should know exactly, like most of the time the loop terminates at a certain point, right? That point that it terminates at becomes a useful property. If it terminates when I reaches m, then you know I is equal to m, and that's like that can be used for replacement, that sort of thing. So typically the negated loop condition becomes a useful assumption, or like just a useful property that you can do this sort of setup with. Yeah, it wouldn't be like, it's not like I don't know if I call it a requirement, but like most of the time you'll need to do, most of the time this will become something. And on the simple mathematical ones where he's doing like addition, or like he has a number increasing, you're just gonna, it's just gonna become abbreviated replacement substitution, and you replace all the terms.
Oh yeah, I just want to mention, Jacob has some really good videos from last year that cover midterm 2 content up to the exam. So yeah, I will paste the link to his channel. So definitely check those out.
Make sure you put the playlist, because the playlist is unlisted.
Yeah, I'll put the playlist. I'll pin it.
Yeah. Supposedly, Kyle has said that. Oh, okay. I thought someone said earlier that he said it'll be given, but we have no confirmation on that. We're not TAs. We got no clue. Okay, well, I think that's a good spot to stop then. Does anyone else have anything else they wanted to say?
So for general proofs, I would recommend just like spamming some theorems that are relevant to the proof, even if you don't think it could lead to something, just like use those, and also be pretty flexible with like random theorems like relation inclusion, relation extensionality, and like other structures like using with or assumption, because those are really like very helpful for some of the questions that will be asked.
By be flexible, you just mean like be familiar with them, like have practiced with them, or
Yeah, and like just make sure you can like catch some like patterns. Like if some question is like related to like relation inclusion, you should like be able to catch that. You need to use it.
yeah, yep, I agree. Yeah, and just make sure like for most questions, you should really be starting at the top and the bottom and working towards like in both directions. It's just really good for part marks, but also I just think it helps you kind of recognize when like you're trying to get the form you're working with at the top and bottom to be the same. Like I was trying to find a good question, but I don't know if I even have a good example here. Oh, this is probably a fine one, right? In this case, I kind of started, or no, okay, this was a weird ass one because I had to reverse engineer what I was even trying to prove. But here we go, this one. Right? In this case, you start with, nope, this is the other proof. This one's mine. This one, final answer, this one. Okay. You have this big complicated expression at the bottom. And so you break it up into simpler terms. I mean, I know you get something longer at the end, but this is a much simpler term and nicer to work with than this. So do you see, I by the end of it, like I kind of had a nice process for it where I would just immediately look at the innermost operator, or sorry, the outermost operator in here, quickly expand it out. Then now I'm looking at something intersected with something, expand that out. You just keep expanding it until you get to your big expanded exists, and you also want your big expanded exists on the top. And now you start to compare what the differences are and to figure out what you need to change to get them to be the same. You really, in most questions, want to be starting top and bottom and try to get them into similar forms. And if they're in completely different forms, you have to ask yourself, like, okay, why are they in different forms? How am I ever going to get them to be in the same form? Yeah. So I hope that helps.
Do any other managers or Gabe, do you have any advice for the second years?
Oh, all notebooks had proof checking on for the past like 2 years for midterm 2 and the exam. Like it was only midterm 1 that had a notebook with no proof checking on it. Like after that, he's always had like every notebook has had proof checking basically. So literally only the first midterm had that one off, assuming the same pattern holds. Like it's only the first midterm has that one notebook with no proof checking, and then everything else from now on should have it. So yeah. No. I'm saying like on the first midterm there was only one. There was just one notebook with proof checking off, as far as I'm aware. Right? Is that what it was like for you guys, or was it different? Yeah, we had theorem lists, we had full proof checking. Everything was like the assignment, was like the homework and assignments. Like it was all just normal calc check, no weird quirks, nothing disabled. It should be like that for midterm 2 and the exam, as long as nothing changes from the past 2 years.
All right, is there any other final remarks anyone wants to make, or is we good to end the session? Yeah, this is all recorded. It's gonna be posted very soon on the CSS YouTube channel. Yeah, thanks. I hope this sort of format was helpful. Yeah, we'll have a feedback form out soon as well. Yeah, you're welcome. Good luck on your tests, everyone. All right.